Okay, so we're going to do section 10.3, which is composite functions, but before we do that, I want to review 10.2 with you. So I have two questions, one multiplication and then another one for division. So this first one here was a diploma example question, and they give you the graphs of two absolute functions, f of x and g of x, and we're looking at h of x, which is the product of the two. Now, f of x and g of x are both absolute value functions, and those are piecewise functions. They're always a little bit tricky to do without looking at the graph. So anytime I have a piecewise function, I like to look at the graph for each one of these. So I'm going to come up with the equation for each one. So I see that they both open downwards, so I know there's been a vertical reflection, and normally the vertex point or the corner is right at the origin, but I see that it's been moved up on both. So I have a vertical translation and I also have a vertical reflection. So let's look at f of x first. So let's get a color here. So for here, this one here is f of x. So it opens downwards, so I know a is negative, and it goes up 2, so I know that the whole graph has been moved up 2 points. So my equation would be negative the absolute value of x and then the vertical translation on the outside. And then I'm going to look at g of x, and g of x right here, I see that that opens up downwards as well. So again, a is going to be a negative, and it's been moved up 4 units. So my equation is going to be negative the absolute value of x plus 4. So I can put each one of these into my graphing calculator, this one in y1, this one in y2, and then h of x is just going to be y1 multiplied by y2, and then remember for the range, we always want to look at that from a graphical perspective. So let's look at this in the calculator. So you can see in y1 I have f of x, in y2 I have g of x, and in y3 I have the product. And I've selected only this one here because I just want to graph h of x. So I want to do that with a standard window setting, so I'll just do a zoom 6. And there's my graph, and you can see it's a really weird graph, a little W there, which is why I wanted to look at this graphically, because absolute values are always a little tricky. So I can see here that it looks like my lowest point is at -1. Just to illustrate that to you, I'll go in here and I'll just graph that horizontal line at -1. And you can see that that is in fact at -1. So it looks like this graph here, which is the product, is everything -1 and greater. So if we go back over here, the answer to this question should now be A. Y is greater than or equal to -1. Okay, in this question here, we're going to be looking at quotient. Now, quotient, just like difference, it's really important the order in which you do these. So you see, we're going to do f of x is the quotient of g over h, and then we're going to look at h over g, and those are not the same thing. So g of x is factored and good to go. Let's just factor h of x. So it's 1 over x squared minus 25, which is just a difference of squares. And I'll factor that as -5 and +5. So in my first example, I'm going to look at the quotient of g of x over h of x. Now, since it's a fraction over a fraction, I don't want to have that. It's kind of an ugly mess. I'm going to use it or write it using the division symbol. So I think this is a little bit easier. So a fraction divided by a fraction. So when we're stating restrictions for division, remember I want those in 3 places: the numerator of fraction 1, the denominator of fraction 2, and also the numerator of fraction 2, because in the next step it's going to become a denominator. So I can see that all together my restrictions are positive and -5. So I'm going to keep my first fraction the same, change the division to multiplication, and then multiply by the reciprocal of the second fraction. Now, as soon as I've done that with multiplication, remember I can make that into one big fraction. Multiplying the numerators and denominators together, I see I have a common factor of x plus 5. So I know that altogether this answer will just be x minus 5, where x cannot equal 2 plus and minus 5. Now let's look at that quotient the other way around. So we're going to look at the quotient this time of h of x divided by, and again I'll use my division symbol, g of x, which is 1 over x plus 5. So again, you can see the same restrictions, denominator, denominator, numerator. So altogether, x cannot equal to plus and minus 5. So I will keep my first fraction the same, change my division to multiplication, and then the reciprocal of the second fraction. So again, with division changed into multiplication, I can use one big fraction for multiplication, and then common factor of x plus 5 in the numerator and denominator. So my final answer will just be 1 over x minus 5, with the restriction x cannot be positive or negative 5. Okay, so let's get into what we're going to do in this lesson, which is 10.3 composite functions. So we're going to determine values, write equations, explain any restrictions, and sketch graphs. So what exactly is a composition? If we have two functions, f of x and g of x, they're defined on some domain of the real numbers, a composition is defined as follows. So this here is what a composition looks like, and the way that we say that is we say f of g of x. So see here we normally have f of x. This time on the inside it's g of x, so it said f of g of x. So it's formed when the equation of g of x replaces the x in f of x, and then we simplify. In other words, the range of g of x becomes the domain of f of x. So I know that sounds really complicated, so I like to think of it just as a substitution. So a composition, I see that as just double substitution, and that's the way that I'm going to show you guys how to do every question, just through a series of substitutions. So let's start with our first one, and I like to start with numbers first. It makes it a little easier. So we have g of x, which is a radical function, f of x is a linear function, and I want to find f of g of 2. So let's just start in the inside. We always want to start inside out. So I'm going to start with this g of 2. What is g of 2? So I know when I say g of 2, I'm talking about the function named g. And the function named g has a variable x, and the rule is I double x, subtract 4, and then take the square root. So I'm going to use that function g, and instead of an x, I'm going to use a 2. So instead of doubling x, I will double 2, subtract 4, and then take the square root. So when I double 2, that's 4, subtract 4 is 0, and the square root of 0 is 0. So here comes my first substitution. F of g of 2, I replace g of 2 with 0 because I just found out that's what g of 2 is. So now instead of saying f of g of 2, I can say f of 0, and that's substitution number 1. So if I'm now talking about f of 0, f tells me I'm talking about a different function. So f is this function right here. And the rule for f is I take x and subtract it by 1. So when I want to do this one here, I'm going to do f of g of 2, and g of 2 is 0. So instead of x minus 1, I'm going to have 0 minus 1, and that is substitution number 2. And then I just do 0, take away 1, and that's negative 1. So I'm working inside out. I found what g of 2 was, and I substituted that as the new x for f of x. And then I took f of x and substituted the new x value, which is 0, and simplified it. So I always like to check these on the calculator to make sure I did that correctly. So let me just show you that. I have f of x in y1, g of x in y2, and this is how I enter in f of g of x. F is in y1, the brackets mean of, and then g of x is in y2. That's different than multiplication. So I want you to know that this is not the same. y1 times y2 is not the same as y1 bracket y2. The calculator knows that that bracket really means composition. So we were looking at what f of g of 2 is. So I look at when x is 2, and you can see here's f of 2, g of 2, and then all together f of g of 2, which is -1, which is what we got. Okay, let's try that again, but instead of doing f of g of x, we'll flip it around and do g of f of x. So same functions. I have my radical function, root of 2x minus 4, and my linear function x minus 1, and I want to find g of f of 4. So this notation here looks a little different than what we had before. So this is an open dot, and I just want to make sure that we're okay recognizing that that open dot really means composition, and these are used interchangeably. So if I were to color that dot in, that would mean multiplication, but an open dot means composition. So remember that. Open dot, that means composition. And let's also write down closed dot equals multiplication, just so we keep those two ideas separate. Okay, so we're going to go the other way around. So I'm going to start on the inside, which is f of 4. So f tells me I'm dealing with function f, and f of x is x minus 1. So f of 4 is 4 minus 1, which is 3. So to solve this question, g of f of 4, I work inside out. So my very first substitution is going to be f of 4, which we just found is 3. So substitution number 1, f of 4 is 3. Now g of 3 tells me I'm going to my function, and that function's name is g. And g of x right here, the rule for that is 2x minus 4, the square root of that. So what I'm going to do here is I'm going to do g of f of 4. F of 4 we just found was 3. So I'm going to do 2 times 3 minus 4, square root of that. And that's substitution number 2. So 2 times 3 is 6. 6 take away 4 is 2. So my final answer, g of f of 4, would just be the square root of 2. So substitute, substitute, simplify. And again, let's check those on the calculator. So you can see I still have f of x and g of x, but notice in this step I do g of f of x, which is why I do y2 first. Okay, so I'm looking at g of f of x, where f of x, it's actually an x value of 4, so g of f of 4. So that's why in my table I'm looking when x is 4. So here is, that's f of 4, this is g of 4, and this number here is g of f of 4. Now we got an answer of square root of 2. You can see on my calculator the square root of 2 is 1.412 rounded, so I know that I did that correctly. Okay, let's try one more with numbers, and then we're going to move away from numbers and use our x values. So I still have g of x is the radical, f of x is still the linear, but this time I want to do g of f of 0. So that open dot again tells us that we're dealing with a composition. So that's just g of f of 0. So step number 1, work from the inside out. So the inside is f of 0. So f tells me to go to that function there. And f of x is x minus 0. So f of 0 is 0 minus 1, which is -1. So now I'm ready to go. So g of f of 0 we just found out was -1. So that is substitution number 1. So now we're doing g of -1. So my second substitution tells me I'm going to function g, which is right here. So instead of using a x value, I'm going to use f of 0, which I found out was -1. So this is going to be 2 times -1 minus 4, all square rooted. So 2 times -1 is -2, take away 4 is -6. So I'm going to have the square root of -6. So that was my substitution number 2, and then I simplified. Well, hopefully you'll recognize that the square root of -6 is undefined because you cannot square root a negative. So since this is undefined, and again I'll add on there, you can't square root a negative. That means that g of f of 0 is also undefined. So since you can't square root a negative, I would say that g of f of 0 is undefined. Okay, so let's move away from the numbers and let's look at in terms of x. The idea is still the same. We're just making substitutions. So composition just means double substitution. So here I have g of x and f of x, same functions I've been using since the beginning. But we're going to do it in general now. So if I want to come up with a general expression for f of g of x, start inside g of x. And I can see up here that g of x is the square root of 2x minus 4. So that's my substitution number 1. So now to do f of g of x, I'm going to substitute the root 2x minus 4 for f. So I'm dealing with this new function f, and I'm going to substitute instead of an x, I'm going to substitute my new x value, which is the square root of 2x minus 4. That's substitution number 2. So the final answer I have to simplify is root 2x minus 4 and then subtract 1 on the outside, and there's really nothing left that I can do to simplify that. So that would be my final answer. Okay, let's look at this same idea, but we're going to flip it around now and do g of f of x. Okay, so g of f of x. So my first substitution is work inside out, and I'm going to substitute f of x, which is x minus 1, to be the new domain. So that's substitution number 1. So now that I'm doing g of x, my substitution is I'm replacing this x minus 1 with that x for function g. So instead of having 2x minus 4, I have 2 times x minus 1 minus 4 with the square root. So that's my substitution number 2. So let's simplify now. This will be distributive property, 2x minus 2, and don't forget you have your minus 4. So that would really be the root of 2x minus 6. And that would be your final answer now that we've done our simplify. Okay, so let's talk domain and range. So I have a radical function and a quadratic function. I want to find the domain and range of f of g of x. So I think the best way of doing this is to do it on our calculator so we can visually see what's going on. So what I'm going to start with on my calculator is in y1, I'll put in f of x, which is the root of x minus 1. In y2, I'll put in g of x, which is x squared. And then in y3, I'm going to do my composition of f of g of x. So y1 of y2. Now, I only want to focus on my composition, otherwise my graph is going to be way too messy. So you can see I've selected the equal sign here, but the equal sign for y2 and y1 are not selected, okay? So I've deselected those. So I deselect those, and when I graph it, I'm only graphing y3, which is my f of g of x. So you can see on the graph here, this is the graph f of g of x. So let's look at that graph and determine the domain and the range. So I can see for the domain there's 2 different pieces, one on the right hand side where x is bigger than 1, one on the left hand side where x is less than -1. So I can write my domain in 2 different ways. So first way that I can write it is in that proper set notation. So that's the set of all x such that x is greater than or equal to 1, or x is less than or equal to -1, but still an element of the reals. Now, if you want to do that in interval notation, you could just say that it would be from negative infinity up to and including -1, or, and that just means or, so this union means or, including 1 up to but not including infinity, positive. Okay, so that's my domain. Let's look at my range. My range is in quadrants number 1 and 2, so it's everything that's positive. So that would be the set of all y such that y is greater than or equal to 0 and still an element of the reals. Or if you want to do that in interval notation, it would be including 0 up to but not including infinity. Okay, so for the next one, I want to look at domain and range, but we're going to switch around f and g. So same functions, but this time we're going to look at g of f of x. So I set it up the same way, but this time I'm looking at g of f. So this is like y2 of y1. So same idea as before, I'm just switching around the g and the f. So again, I don't want these two selected, I only want the last one selected. Okay, so I deselect y1 and y2, and then I end up with this graph. So let's talk domain and range. So I really like to look at the graph, especially with composition, because they can be a little bit complicated and tricky. So when I see it on the graph, much easier to see. So the domain is the set of all x such that x is greater than or equal to 1, but still an element of the reals. Or if I want to, in interval notation, I can say 1, including 1, up to but not including infinity. And then for the last one, the range is all the y's are positive, nothing negative. So it's going to be the set of all y such that y is greater than or equal to 0, but still an element of the reals, or using interval notation, 0 up to but not including 0. Okay, so we've looked at composition with numbers, we've looked at it in general, we've looked at domain and range. So the last two examples I want to look at is, if I give you the composition, can you identify the inside and outside functions? Okay, so this one here, I'm giving you h of x, which is f of g of x, and I want us to determine f of x and g of x, possible expressions for each. So h of x is the composition. Now, compositions are made up of inside functions and outside functions. I can see that g of x is the inside function and f of x is the outside function. So that's how I want to look at this, okay? So I'm going to say that g of x is inside, f of x is outside. Now, it's important to note that there are several answers for this, so answers vary. I'm just going to go with what I think is the most basic answer. So h of x is the composition, so I'm going to look at the outside function and the inside. I think it's easiest to identify the inside function. And what I mean by inside function is it's what's replacing just a plain old x. So I can see that this is 2x plus 3 all to the exponent of, that should be a 5, my mistake, that should be a 5. So it's 2x plus 3 all to the exponent of 5. So I can see the inside function is just that 2x plus 3. The outside function is going to be, what am I substituting x for to get the composition? So the outside function would just be x exponent 5. So we can check that, because if I were to substitute 2x plus 3 in for this x, I would end up with 2x plus 3 to the exponent of 5. So just go with the simplest way of doing that. And again, there are other answers. I think that this, I just want to go with the simplest one. So let's try one more. So the function h of x equals f of g of x is given below. So this again is my composition function. So again, I want to think inside, which is g of x, outside, which is f of x. So in doing this here, I'm going to do this. So h of x is 1 over something. So that something is 3x minus 1. So I think of g of x as that inside function, which is 3x minus 1. F of x would be the outside function, which I see as 1 over x. So what I mean is, if I were to substitute g of x in place of that x there, I would end up with my composition function here. So think inside, outside. Again, answers can vary. This is just one possibility. Okay, so we've seen composition from a whole bunch of different angles. So to summarize, compositions, they are just a series of substitutions, usually 2. And so I just think of compositions as a double substitution. I want you to remember to work your way inside out. Because they are double substitution, I want you to use brackets, especially if there's any negatives or subtracting. Any domain restrictions you have for one function carry throughout the entire function. Because the graphs, the compositions are a little bit more complicated, I really advise you to look at the graph. So look at the graph to verify any domain and to determine the range. We always do range on the graphing calculator. So this is our last topic that we did in chapter 10 for functions. And I'd like to thank math teachers for putting the fun in functions since the beginning of time when t equals 0. Okay, so to do practice questions, I want you guys to do, wow, 1 to 53. That's a lot of questions. How about we just say 1 to 5? Wouldn't that be nicer? Let's do 1 to 5 for the practice questions. I have detailed solution for all my practice questions on D2L. And then after that, I want you to move on to the textbook and try some of those questions. So that's it for functions and chapter 10.